Hello, I hope you had some time to process that last example, took a break, got a good snack, got a stretch in, and now we're going to do another example. This will be our last one in the notes, and then I'm going to do one more example, probably in another video that's not in the notes. It's just going to be on another sheet of paper to help you when you go to your assignments. But for now, this is the last one in the notes. When we look at this one, it says find the area of the region bounded between the graphs of 2y squared equals x plus 4 and y squared equals 5. So before we jump into graphing those, when I look at that problem, because if you notice in this one, we don't have y or x alone. Because normally a shortcut in these type of problems to know what you're going to do is if you have y alone, if it's in terms y equals for both equations, you should do vertical lines and do top minus bottom. If you have x alone for both your equations, then you would do right minus left and draw horizontal lines. But now if you look here, we don't have y or x alone, so it's kind of maybe difficult to know which one you should get alone. But if we look here, we have x alone, so that kind of tells us maybe we should get x alone here and do horizontal. Another thing is to think about if this y is being squared, if you were going to get y alone, you would have to square root, and then we would have plus and minus that came up in that first example we did, and we wouldn't want that. It would be too messy. So anytime you have y squared, keep it in terms of y and get x alone. So let's go ahead and do that. We're going to do minus 4. So our equation becomes x equals 2y squared minus 4. And then we have this one right here. X is already alone, but I'll rewrite it so we have it. X equals y squared. So what do we know? They're both y squared, so they're both this horizontal quadratic that we talked about before. This one's just the original one, but this green one is vertically stretched, and it's going to be shifted to the left 4. Remember, now that it's horizontal, the sign doesn't switch. If it's minus, it's going to be shifted to the left. If it was positive, it was shifted to the right. So let's go ahead and see if we can get a sketch of these on a graph. I'm going to go and draw the green one first. So I'm going to go to the left 4. And again, sometimes before you sketch, if you don't know where to start, it's easier to get the intersections first. I don't know, I go back and forth. And then I'm going to just draw a horizontal quadratic opening up to the right because it's positive in front of the y squared. And now it does have a stretch to it, so I wouldn't really worry about that when you're sketching it necessarily. And then we have this y squared, which starts at the origin and still opens up to the right. So it's kind of like, how do these intersect? But again, it might have helped if we did that first. But it's going to look something like this, because that's going to be wider since, oops, that kind of looks like more of a V shape, but it's supposed to be a quadratic. And so what are these points right here? If we go ahead and set these equal and get our intersection points, it might make more sense. So if we take 2y squared minus 4 and set it equal to y squared, well, let's move everything over to, let's say, the left side. You could do either one. If I do minus y squared, then we end up with 2y squared minus y squared would be y squared minus 4 equals 0. So you could solve this different ways. You could use difference of squares, or you could move over the 4 and then square root. I like difference of squares because it makes sure you get the positive and the negative. Sometimes you'll forget the plus or minus if you do the other way. So, oops, the square root of 4 is 2. So the factors are positive 2 and negative 2. So that makes your intercepts negative 2 and positive 2. So notice those are y. So we have these two intersection points here, and one is down here at y equals negative 2, and one is down up here at y equals positive 2. So how do we know that? We don't really need to know that x value, but if you wanted to, you could plug it back in to either one of these formulas. I'll use this one. So when y is 2, if I square it, my x is 4. And same thing here, if y is negative 2, when you square it, x is 4. So these are both at x equals 4. but we shouldn't be using that number when we set up our integral because it's all in terms of y. Okay, so if we look at this area we bounded when we drew this shape, we created this area and we should be drawing horizontal lines because it's in terms of y. So when you draw these horizontal lines, you should be thinking right to left. I was just drawing them left to right, but really when you set up your integral, you're going to set it up right to left. So does it stay consistent? You should always ask yourself, draw some lines and say, does it stay consistent, the right function to the left function, which in this case it does, right? You start on the red function and you go to the green function for this whole shaded area. So that means we get to set up only one integral. So our area would equal the integral, and now what's the lowest y value you go to is at -2. To the highest y value you go to is +2. And then we shaded right to left, so our right function was the red, which was y squared, minus our left function, which was the green, which was 2y squared minus 4, which always put those in parentheses. I almost didn't, which would have been bad. So I would have messed that up. Because why is that bad? Because then you wouldn't distribute this minus sign, which I'm going to go ahead and do. So this becomes y squared minus 2y squared plus 4. And now you can, or we can go ahead and combine these like terms, before we integrate. So it becomes -y squared when you combine plus 4 dy. And now integrate, which this would be a great place to pause. Do it on your own. I can go ahead and do it, but again, don't feel free to fast forward if you do it on your own and just check your answer. So when I take the antiderivative, add 1, divide the coefficient, that'd be -1/3 y cubed. Antiderivative 4 would be 4y. Your boundaries are -2 and 2, so now we plug them in. So we have -1/3 times 2 cubed plus 4 times 2. That's f of b. Now you have minus f of a, so -1/3 times -2 cubed plus 4 times -2. Now we clean this up. So that would be -1/3 times 8 plus 8 minus, I think I'm going to go ahead and clean this up before I distribute, so I'm still going to put my parentheses. -2 cubed is still -8 times -1/3, so that becomes +8/3. And then 4 times -2 is -8. Okay, so now I could have gone ahead and multiplied those together, right? So this would be -8/3 plus 8, and then distribute this minus sign, so -8/3 plus 8. Okay, so you could go about this probably a couple different ways. You could go ahead and add your 8s, or go ahead and just put them both over 1 and get all the common denominator. I think I'm going to go ahead and, what did I do here? Combine my 8s and my 8/3. So this becomes, if I combine this 8 plus this 8, that's 16. And then minus, if I go ahead and add these two fractions over 3, -8 minus 8 would be -16 over 3. Correct? Okay, so now I need a common denominator. So I'm going to put my 16 over 1, and I need to multiply it by 3 on the top and bottom. So 16 times 3 becomes 48 over 3 minus 16 over 3, which 48 minus 16 is 32 over 3. And that is the area between the two curves. Okay, so let me know if you have any questions on what's happening, what we're doing. Hopefully you're going back to those original formulas and doing, if it's in y equals in your functions in terms of x, you do top minus bottom and you use the x-intercepts or the x boundaries. If it's x equals in terms of y, you draw horizontal lines and you do right minus left, and your boundaries are your y intersects or your y boundaries. Let me know if you have any questions. I'm going to do one more example that's not in the notes on a next video to help with a question that's going to be on your assignment, so make sure you watch that.